everybody. This is the second part of the notes for the Riemann sums, and we're going to talk about taking this Riemann sum idea, this approximations, to actual calculus where we find exact values of areas under curves, which is really cool. And today I'm going to teach you how to get your calculator to help you, but there are some things that need to be explained first. So from the last video, and we don't need this anymore, but from the last video, we talked about, using three rectangles to make an approximation. It'd probably be an under approximation here. And I want you to think about, just consider what would make our approximation better. And one of the things that would make it better is what if we had used 6 rectangles instead, right? If we had used 6 rectangles and each one of them had a height over here on the left as we started with, we would definitely get a better approximation for that. And if we used even more rectangles, we would get even less of this area unaccounted for, less and less of an under approximation. Okay, I'm going to quit drawing them because they're just looking horrendous right now. But more rectangles, we get a better approximation. And ultimately, the number of rectangles that will give us the actual value under the curve is an infinite number of rectangles. So we're going to look at a couple different ways to say this. And then, like I said, we'll let our calculator do the hard work, and we'll learn how to do the hard work in another couple videos. Okay, so we're just saying, remember n was the number of rectangles that we used, and we said if you didn't know how many you needed, the width of each rectangle, you could take, I think we did 4 minus 1 because that was the interval endpoints, and divide it by 3, and we got that each one should be 1 wide on the other video. This just tells you the change in x, the width of each rectangle, this distance, right, that we were looking at here. Okay, so let's go ahead and say that we want to use n as the number of rectangles. Let's use an infinite number of rectangles, and then we'll use values where we go from 1 to infinity in this old summation notation. And I hope that you recognize here that delta x is a width, and an f value at any width would give you a height, right? So this is just base times height. That's all this is representing. And you should write that if you think you might forget, because this can get tricky if you lose track of your roots here about what this Riemann sum is. It really is just a rectangle area. And I wrote that backwards, so I'm going to white it out and write it again, that it's actually this y value was the height, and this was the base, right? The change in x, the width. Okay, and like I said, we're going to get an infinite number of rectangles. Now, what that looks like in calculus is we're going to take this whole big, clunky, awful thing, and we're going to say, hey, that is not an F without the bar on it. That's actually a big old S for sum. This is summation notation. In calculus, we just write a big old S, and we're going to sum up a bunch of rectangles over an interval. In this case, our interval is 1 to 4. I'm just going to keep it general and make it a to b, and then we're still going to have a height that's going to be determined by a function value. And instead of delta x, remember the old days when we had our slope, we used to say change in y over change in x, and now our instantaneous slope, we use the derivative of y with respect to x, right? So instead of the delta x, we're just going to use the dx here. And I'm going to let you play around with that in your calculator today. And like I said, we'll get to how we could do this by hand pretty quick. Alrighty, another way that we could look at it, I believe the book uses this notation, but another thing that you could do is let the width of each rectangle go to 0. And I think you can see that that's really the same idea here, because as the widths get smaller and smaller, that means we're going to have an infinite number of rectangles. So these two, you can use either notation. I've seen this, I see this more. I believe this is what your book uses. Okay, but 2 ways to say virtually the same thing. Alrighty, so let's go ahead and take some Riemann sum notation. You got a couple of these on your homework tonight, or tomorrow night. The Riemann sums notation, to get it to calculus notation, we're just going to kind of look at this idea, and you can pause me if you think you got it. Try it. This is a sum over the interval, summing a bunch of rectangle areas, right? Height times base on the interval 1 to 3. And where we see this, that represents our height, I'm going to put 2, and instead of the c of k and all this stuff they're doing, it's just our x, right? That's just our x value. And so this is our function. And then instead of delta x, we'll write dx. And it's that easy, and then I'll show you how to get that in your calculator, right? So you don't have to look at this and do approximations anymore. You can change it to calculus and use your calculator. And go ahead and pause me and try to do the last one here. This is all just implying we're summing up an infinite number of things. That's what an integral, this is integral notation, that's what it means. We're summing up an infinite number of rectangles on this interval. And I'm going to just take out all that ugly stuff and just make it a nice 3x squared minus 2x. These are just representing your x values. And then instead of the delta x, we do dx, and that's what we're going to put in our calculator. All right, so let's get working on that calculator and see what we can come up with. Okay, so here we go. We're going to sketch a quick graph, shade the indicated region, then use your calculator to find the numerical integral. So first thing you should do is get your calculator and make sure that you truly are in radian mode. In calculus, you should be in radian mode and just never look back, please, okay? And let's go ahead then and look at the first one. We're going to graph a parabola on that interval. So go ahead and do that. Hey, there you go. And it's going to look something like this. And we're going to look at this integral. And remember, we talked about the train, that this, this idea that an area under a curve, that's all we're talking about when we're looking at these integrals. We were using Riemann Sums rectangles to approximate the area, but now we're going to find it exactly with an integral. So an integral finds the signed area. So let's take a look at this. We're going to go math button. I'll try to get it so you can see this. It's your math button. You're going to choose option 9, fnint. It's a numerical integration. So you're going to choose 9, and then you're just going to plug it all in just as it looks right here. So we'll go 0 to 2 of x squared with respect to x, and we can enter, and I'm getting 2 2/3, it looks like. All right, go ahead and do the other two. You should pause me and give this a try, because there's a couple things. There's something you need to notice in these first examples, so please notice it. All right, and what needs to be determined is why is the answer to number 2 negative. So you should pause me and take a stab at why. I mean, they look exactly the same. What about these integrals made this one negative? So some people would say that our upper bound was less than our lower bound. So I'm going to write this down here real quick and we can look at it. Yeah, if we're looking at this one, we're integrating from 0 back to -2. Whereas in this one, we integrated from 0 to 2 left to right, we got positive. And this one, -2 to 0, left to right, we got positive. But in this one, we sort of integrated backwards, which gave us a negative result. You have to know that. You have to understand that when we integrate from the right to the left, when this bound is actually bigger than that one, that we are going to get a negative some of the time. Okay, let's go ahead and look at the some more of these, and we're going to have you should pause me. I mean, you really got to learn this stuff. I'm going to expect that you've got it when you come into class. So I'm going to, ask you to please pause me because I'm going to just reveal the answers right here. So give it at least a shot here of the same idea. Sketch it, shade it, use your calculator to integrate it. All right, sketch it, shade it, use your calculator to integrate it. You've got to practice. Okay, so when I do this, I got these pictures going. And we'll talk about the integration results here. Integrating 0 to pi, that just means the area under the curve of sine x, the area under the curve of sine x on 0 to pi. And I will point out that this is signed area we're talking about, because clearly it could be negative. We got some negative results a minute ago. So this is our signed area. And we need to really practice on figuring out when it is signed positive or negative. So I'm integrating on 0 to 2. My calculator tells me that answer is 1. I do expect it to be positive because I am going from left to right. Great. Okay, I'm going to go ahead and find the signed area between the curve and the x-axis. I'm not going to use Riemann sums and make all kinds of rectangles. No, thank you. We're going to let our calculator do the hard work. I'm going to integrate, it says, from pi to 2 pi this way. And I got a negative answer. I want you to consider why that would be negative. Why would your calculator, I'm going left to right. Why in the world would I get a negative signed area there? So think about that. This one, integrating 0 to 2 pi, I get a 0 area. Think about that. You're going to have to be very good at why that's 0. And pi to 0, kind of expecting a negative on this one, just like we got above. And it would be negative 2 because we didn't integrate from right to left. And then we're going to integrate from 2 pi to pi. Once again, I'm going right to left, so it's backwards, but lo and behold, I actually get a 2. Kind of weird. And then I'm going to look at this one also from 0 to negative pi. So I'm integrating again backwards, right to left instead of left to right. And for some reason, though, I'm getting a positive answer. Why? Why is that happening? Okay, some reasons why. Some answers are negative and some are 0. And I'm just going to kind of bullet and jot some things down here. Is that if the area is under the x-axis, the area that you shade, the area is under the x-axis, it looks like in which one? There it is, this one. We integrated perfectly fine from left to right, but because the area was under here, it was signed negative. Okay, because it's under the x-axis. So that might be a reason we would get a negative answer. Another reason would be just integrating the low bound is bigger than the upper bound, integrating from right to left. That's another reason. So this one, area, we're going left to right just like, we want to, but because the shaded region is underneath, we get a negative area. This one, integrating backwards, right to left, the area is above, but we're going backwards, so we end up getting negative. And I think the interesting one is this one and this one, because we're integrating backwards, so it should be negative, but because we're under the x-axis, it really is that negative and a negative make a positive, right? And the same here, integrating kind of the wrong way, backwards, right to left, and because the shade area is under, we're going to get a positive answer. And we're going to get a 0 answer when the area above the x-axis is the same as the area below. And they really do just kind of cancel each other out. Okay, so I'll get you where you can see those here, and I'm going to stop this recording.